In this module, we will begin our study of statistical mechanics. And the motivation for doing this is the fact that in engineering, most of the systems that we're going to be dealing with are going to contain a large amount of molecules. Basically, we know that for 1 mole of some sort of chemical, that means there are about 10 to the 23 molecules within that system. And so, a lot of the systems we're going to be dealing with, almost all of them, are going to contain, an unfathomable amount of molecules within the system. And these molecules are not going to be static, but in fact, they're going to be moving around constantly, whether we're dealing with gases or liquids, even in solids materials, there's going to be sort of molecular vibrations that we're going to have to deal with. But whenever you do a measurement on any of these systems, a macroscopic measurement, so if you measure temperature or if you measure density, things like that, you'll typically observe that these properties are going to be stable, right? And the reason for that is because whenever we do a measurement, or at least relative to the molecular motions, which occur on timescales ranging from femto to nanoseconds, the timescale of the molecular movement is going to be much shorter, or typically much shorter, than the measurement we actually perform on the system, so on the macroscopic measurements. Okay. All right, so this is both what is observed in an actual experiment, and it's actually even observed when people do sort of simulations, molecular dynamics simulations, or Monte Carlo simulations. And so one example of this would be what's known as a Lennard-Jones fluid, which is just a very simple model for describing liquids or gases computationally. And so for example, here's some data for a Lennard-Jones fluid in which the folks who did the simulation, they calculated the potential energy in what are known as reduced units, so it just kind of normalizes the potential energy. They calculated the potential energy for this Lennard-Jones fluid as a function of time, right? And so we see at the individual time points that the potential energy, kind of varies, right? Here it's high, here it's low, and the potential energy is going to kind of fluctuate constantly over time, right? So at the individual time scale, we see that the potential energy is changing quite a bit. But if we kind of zoom out and we think about the entire sort of time range in which the measurement is being done, we see that the potential energy is basically fluctuating around some sort of average value, right? And so in an actual experiment, rather than measuring the individual potential energy at a very specific time point, what you do is you get a temporal average of that potential energy, right? And so that's what you would detect in an actual experiment. And so, recognizing that sort of contrast between what's going on at molecular timescales versus what's going on at macroscopic timescales, that's where statistical mechanics finds its utility, right? And so with statistical mechanics, what we're going to do is we're going to study the properties of ensembles of molecules, right? So a large group of molecules together, okay? And by doing this and developing mathematical tools to describe these ensemble of molecules statistically, that's going to allow us to make predictions about the average value of various thermodynamic properties. Average values of thermodynamic properties. So we can not only get what the average value is here. But we could also, since we're trying to describe this behavior statistically, we could also see, in general, how much the thermodynamic properties vary, or how much they deviate from that average over time. So if we make a specific measurement, we could see if that value that we measure is statistically different than what we expect, or if it's within error of the average value.